Recall our sinusoid, our trigonometry functions, and if we draw again our cosine function, we have a cosine of x, and cosine was going from 1 to -1. We would start here and it would go down and up again, slowly down and then up. And this actually looks like a wave, a sound wave or a magnetic wave or anything that resembles something with a frequency or a period. So our question is, can we actually mathematically transform this function into something so we can play with it a little bit? And it turns out, of course, yes, we can. So we have a sinusoid which has a structure of a times the cosine of omega t plus phi. Well, what does everything mean? Well, let's explain that. Of course, as first we have a, and a represents the amplitude. What does the amplitude mean? The amplitude just says something about how high our function goes. Right now, with this cosine in front of here, we see that it only goes up to 1 because the a in this function is actually 1. If I put a 2 in front of it, my maximum is at 2 and my lowest is at -2. When I put a half in front of it, its maximum is a half and it goes down to -1/2. Before I talk about omega, let's talk about phi, because phi is our phase shift. Phase shift just means that you are shifting your sinusoid along the x-axis or the real axis if you talk about complex trigonometry. Shifting it to the left or shifting it to the right. And as we had seen before, that if we shift our cosine function to the right, then we actually retrieve our sinus function. So the phase shift just says something about how much we shift to the left or the right. The omega is called the radial frequency. And this has unit radians per second. This radians per second can be rewritten to calculate other things. For example, we can calculate the cyclic frequency with omega divided by 2 pi. This is your cyclic frequency. With as unit hertz. And hertz just says number of periods in 1 second. In 1 second. Well, what is a period, or how do we calculate that? Well, period is capital T, is just a piece of our function that repeats itself. So if we look up here, if we can cut it here until here, this piece repeats itself over and over. We could also say, well, from here to here is a period. We could also take it arbitrarily here and say it is upon until here. Oh no, excuse me, up until here. It repeats itself over and over again. So that is a period. It's a pattern that has small building blocks that just repeats the block over and over again. And that can be calculated with 2 pi divided by omega. And this is 1 period length. So the length of 1 period denoted in seconds. And from this we can deduce or derive that frequency and period are intertwined or related to each other, because the frequency is 1 divided by the period and the period is 1 divided by the frequency. Now, it is also important to note that our phase shift is between -pi our phi and pi. Because if we add up 2 pi or 3 pi, it is the same as adding 0 or pi, relatively. So before we saw with Euler's formula that we can rewrite sines and cosines into complex exponentials. And that is also something we can do here, which have their own benefits. In the next video, I will show you another way of rewriting these sinusoids, but for now, we are using this as follows. Suppose we have two signals, namely cosine of let's take t plus pi divided by 2, and we have another function x2. Let's write it down here. x2, which is 3 cosine t minus pi over 2. And we want to add these two cosine, or these two sinusoids, into a new sinusoid. We want to create a new one. If we add two sinusoids together, it's actually representative by another sinusoid. And our question is, well, how can we do that? How can we rewrite this as one sinusoid? Well, first what we do is we are going to rewrite both of these signals as complex exponentials. I to the power of omega t plus phi, excuse me. This is how you're going to rewrite it, because if you recall our Euler's formula, which was e to the power ix is equal to cosine of x plus I times the sine of x. Right now we just have the cosine, and this in itself is actually a Cartesian form of a complex number. Actually, our cosine that we have is just the real part of this number. So we can assume that we are just looking at the real part of this number. And with that, it's actually easier to compute the following. If I want to have one signal of this plus x2 to calculate this, it is easily done with this formula, and assuming we are just looking at the real part because we have cosines. How are we going to do that? Well, first we're going to rewrite both into a complex exponential. For x1, we're going to say that we are looking at the real part, and we're just filling in what we have up there with the formula of Euler, saying that we are just looking at the real part because we just have the cosine, so it's not actually the whole Euler's formula, it's just the real part of Euler's formula of I to the power of t plus pi divided by 2. And that's it for x1. For x2, rewriting it is saying we are looking at the real part, and we have 3 times e to the power of I, and filling in what is inside the brackets here, we just get t minus pi divided by 2. It's very straightforward, like this. Now it's time to add them together. So let's do that in Cyan. Let's say we have xt, which is right now the real part of e to the power I t plus pi divided by 2 plus yellow plus 3e I to the power t minus pi divided by 2. And we can add these real parts together effortlessly because they are both a real part. So we can just say if I have real part of the one and real part of the other, if I add them together, I'm still looking at the real part of our number. Well, let's rewrite these. I need a little bit more space. Let's rewrite these functions. So we get the real part of e to the power it plus I times pi divided by 2 plus 3 e to the power it minus I pi divided by 2, close the bracket. Now what are we going to do is we're going to split up these powers and try to get an e power out of it. So this is equal to the real part of e to the power it times e to the power I pi divided by 2, because multiplying these numbers together is adding the powers, so we can also split them up, plus 3 times e to the power it times e to the power minus I pi divided by 2, like that. Now we can take something out of the brackets, because both terms contain some stuff. First, we can take out e to the power it. And if we look closely, we can actually also take out e to the power I pi divided by 2, where we are left with 1 plus 3 times e to the power of minus I pi, like that. Because if we multiply this with this, means we have to add the powers together, and minus pi plus a half pi is minus a half pi, which gives us back what we had originally. You can also do this in 2 steps. First take out e to the power it and then see what you're left with. But for now, we have taken this out and we are almost finished already. So we're still looking at the real part, e to the power it. Let's already add these powers together. So we get I pi divided by 2. Open the bracket, we get 1 plus 3 times, well, here we have e to the power minus I pi, and that actually is a polar number. And we want to know to what number is it referring. Well, if we look at our plane again, like this, we have a distance of 1. And what is our angle? It's pi. Well, if we start here, pi is all the way on the other side. It is here with a distance of 1. So the point we are actually looking at is minus 1, comma 0. Or better said, minus 1 plus 0i, actually. So just minus 1. So this number is actually just minus 1. So we can multiply this 3, not with e to the power minus I pi, but with minus 1, because that's actually the same thing. Now rewrite what is in the bracket, because now we can add 1 plus 3 times minus 1. It's e to the power it plus I pi divided by 2. Here we get 3 times minus 1, it's minus 3. So we get 1 minus 3 is minus 2. So this is 1 minus 3, and 1 minus 3 is minus 2, so we multiply with minus 2, like this. There's just 2 more steps to make. The first step we have to make is taking the I out of the brackets, so let's also put minus 2 in front of it, and we get e to the power of I t plus a half, pi divided by 2, I mean, like this. And now, because we're just looking at the real part, we can actually translate this back into a cosine. Namely, this is equal to minus 2 times the cosine of t plus pi divided by 2. Like that. And now we have added 2 cosines together into 1 cosine. And this cosine is exactly the same as the cosine shown before. The two cosines added together. If we were to plot these two cosines added together and plot the cosine we just calculated, it is exactly the same. And this is one way in writing your sinusoid, in this case your cosines, into adding them. And in later videos, we will see that this method is only used for adding the cosines together. And we will use a third method to write down our complex exponentials in a better way to help you with calculating the frequencies. So this is all we have done, just adding those two sinusoids together.